Welcome to this Advanced Higher Physics Electromagnetism Unit video, and this particular video is looking at charges experiencing forces in uniform electric fields between parallel plates. So we will be covering the use of appropriate relationships to solve problems of the motion of charged particles in uniform electric fields, in effect the equations of motion, and equals V over D and F equals QE, and Newton's second law. And we'll also briefly mention at the end the consideration of the electron volt as a unit of energy and conversion between joules and electron volts. So if we have parallel plates, then between parallel plates we have a uniform electric field. Towards the edge of parallel plates we do have fringe effects, so you can see that the lines are straight within the parallel plates, but at the edge they are slightly curved. But parallel plates are used for this case because they provide a constant electric field strength at all points in the field, and that means that the force that a charge experiences will be the same at any point within the field too. We've seen earlier in a previous video that a charge in an electric field will experience a force, and the magnitude of that force, F, is equal to Q times E. In this situation, the electric field strength is uniform compared to the electric field strength around point charges. Electric field strength can be measured in newtons per coulomb because it's equivalent to force divided by charge. And we can compare this to W equals mg, where we've got the force equals the mass times the gravitational field strength instead of the electric field strength. So the work done given on the charge in the field is Q times V from higher physics, and work done is also equal to force times distance. So because F equals Q times E, then we can end up with QV, where V is the potential difference, is equal to E times Q times D. And so we can cancel out the Q's there from both sides to end up with a relationship that the potential difference is equal to the electric field strength times the distance between the parallel plates, or the electric field strength is equal to the potential difference across the plates divided by the separation between the two. And that's quite common for this type of situation, to work out what the electric field strength happens to be. Divide the potential difference by the separation between the plates in meters. Okay, so let's look at a problem of a charge in a uniform electric field. So we've got charge Q here. This is actually a charged oil drop, and it's placed in a uniform electric field between two parallel plates. And we're provided with the mass of the oil drop and the charge on it. It's got a negative charge of minus 6.4 nanocoulombs, and the parallel plates are 5 centimeters apart. So potential difference is applied across the plates to produce the uniform electric field, and we're asked to work out the electric field strength. So the electric field strength, as we've just seen, can be worked out from the potential difference and the separation between the plates. And we're also asked to work out the electric force acting and the direction of that force. So let's start at the first problem here, looking at the electric field strength. So we've just seen that the electric field strength, E, can be calculated from the potential difference divided by the separation between the plates. So if we divide 400 by 0.05, 5 centimeters, we can get electric field strength of 8,000 newtons per coulomb. We could write that unit also as volts per meter. Both are acceptable units for electric field strength. Calculate the electric force. Well, we know F equals Q times E. And so if we multiply that 8,000, our field strength, charge that we have, we can end up with the force in newtons. Now, because we've got a negative charge and the polarity of the top plate is positive, the direction of the force will be upwards. So we are going to consider the weight and determine the magnitude and direction of the unbalanced force acting on the ore drop, because there are two forces acting on this drop. There is the force due to the electric field upwards, and there is the weight or gravitational force downwards. And having determined if there is an unbalanced force acting, we can calculate the acceleration of the ore drop. So the weight can be calculated in the usual way. W equals mg, multiplying the mass by the gravitational field strength. And we can see that the weight is significantly an order of magnitude greater than the electric force due to the electric field. That was 5.12 times 10 to the minus 5 newtons. So we can find the unbalanced force by taking those two forces away from each other. And we end up with an unbalanced force of 1.45 times 10 to the minus 4 newtons, which is downwards. We can then work out the acceleration, or the initial acceleration of the drop, using Newton's second law. So let's consider Robert Milliken, an American scientist's experiment, and he used ore drops to determine the charge on an electron. He sprayed oil drops, negatively charged oil drops that were ionized by ionizing radiation, into an electric field. And what he did was he adjusted the voltage until the force upwards within that uniform electric field balanced the weight of the oil drop. And by determining that, he could determine what the charge was on the oil drop, and he found that the charges were multiples of the same particular value, 1.6 times 10 to the minus 19 coulombs. So the oil drops are sprayed into the top. His experiment actually ionized the oil drops in the top there as well, using some alpha radiation. The oil drops then fell down at different rates depending on what size they happen to be, and some of them fell through the gap at the bottom here, and he looked at this and he adjusted the potential between the plates and he changed how they fell. And he either changed it so they were stationary, or he changed them so they fell at a constant speed, because both of those situations show that the forces are balanced. By looking at the size of the drop, he could work out its weight, because most of the drops were circular in nature. So you've got a sphere of oil, and if you know the density of the oil and you know the diameter of the sphere, you can work out its mass from its volume and its density, and then knowing its mass, you can work out the weight of it. So that's what he did. So he had these drops and he ionized them. They fell through the gap into the uniform field. He adjusted the potential difference across the plates until the forces were balanced, and then he looked at what that potential happened to be to work out what Q was. Okay, after thousands of measurements, he found that the charge on the ore drop was always a multiple of the basic unit of charge that we now know, 1.6 times 10 to the minus 19 coulombs. So it was either one of those, or two of those, or three of those, depended on the amount of ionization that had taken place. Okay, let's move on and look at projectile motion of charges in a uniform electric field. These can be solved in very similar way to we would solve horizontal projectile motions in gravitational fields. So we can have a charge here that is moving from left to right within this particular plate. It might be following this curved path, and it would follow that curved path because if it's a negative charge, it's attracted to the bottom plate there, and so it's going to follow this curved path, and if it's entering this field moving already from left to right, it's following a curved path just like a projectile, and we can solve it in same ways like we do our normal projectile the horizontal velocity will be constant because there's no forces on it, in the same way that horizontal velocity of a projectile in a gravitational field is constant because there are no forces acting on it. And there will be a downwards force due to the electric field in this case, whereas usually there's downwards force due to the gravitational field. And so we can apply the same thing because there's a constant unbalanced force downwards. There is a constant acceleration downwards, so we can use our equations of motion to solve problems like this. Okay, so electric fields will produce this type of situation. If we have a charge within a magnetic field, then we will get circular motion taking place. And sometimes we use both fields together to direct charges to where we want them to go to. So let's have a look at an example of an electron deflection tube. So these are partly parallel plates, and we've got an electron that's going into this uniform electric field, and the plate at the top is positive, so the path of the electron is curved upwards. And the electron is initially traveling perpendicular to the field. Now we can ignore gravitational effects because when we work out the weight of an electron, we actually find that is insignificant compared to the force due to the electric field. Some questions ask you to do this so that you are comparing the two values, and you can see that you don't need to take it into account. In the case of our previous example, we did need to because it was an ore drop, so it had a fairly significant mass. So we have a load of questions that we need to look at here. We're going to work out the time taken for the electron to move through the field from the left side to the right side, and then determine the acceleration and the vertical displacement. So how far has it moved up at point X? And then there's a situation where we're asked to explain what will happen if we increase the potential difference to the position of the electron and justify our answer. Okay, so let's look at these questions one by one. So if we want to work out the time to move through the field from the left to the right, then horizontally there are no forces acting upon it, and we're given the velocity at the top of the page here, 2.7 times 10 to the 7 meters per second, and we're also given a distance that it is between these two plates, so we can simply use speed, distance, time to work out the time that the electron takes to go from the left to the right. Okay, we're then asked to work out what is the vertical acceleration of the electron. So to know the acceleration of the electron, we need to know the force. And so we're going to use Newton's second law, A equals F over m, where the force is due to the electric field, which is also QE. This time we aren't given the strength of the electric field, but we are given the potential difference, 1.9 kilovolts, and the separation between the plates, 105 millimeters. So this is showing all the things added together, but it might be quite usual for you to say, well, actually, I'm going to work out my electric field strength equals V over D first. And then once I have my electric field strength, I can work out my force, which is Q times E. And then I can divide that by the mass. So you don't have to do all of the steps of the calculation at the same time that is shown here. Okay, the next part asks us to work out the vertical displacement of the electron at point X. And there are 3 marks for this question, which is why there's a 3 there. And to do that, we're saying, well, there's a constant acceleration. We've just worked out what it is. There's a time, or we've worked out what the time is, the time for the vertical motion is the same as the time for the horizontal motion that we got from speed, distance, time. And so we can use an equation of motion because we have a constant acceleration and the displacement is s. And because we don't have v, we don't have the final speed, we don't know what it is yet. We could work it out, but we don't have it yet. Then the best relationship to use is s equals ut plus half at squared. Worth remembering that we're not using the horizontal velocity up the top here. Okay, that isn't the right value to use for our initial velocity because that's horizontal rather than vertical. So our initial vertical velocity is 0 because the electron is not moving upwards at all until it enters the uniform electric field where it experiences a force upwards and starts to accelerate. So it's worth remembering that u will be 0 in the same way that when you're working out projectile motion at higher, that you have to consider what the initial velocity in each direction happens to be. So it works out we've got 1.6 centimeters, 16 millimeters of movement between the central path that we've got and point X. And the final part we were asked to consider is if we increase the potential difference, whether the electron will leave the field higher or lower or in the same position. So what is happening? So, well, let's consider our earlier answers. So the first thing we did is we worked out the time. So the time is going to be the same in this case. Second thing we did is worked out the acceleration. Well, the acceleration depended on the force, and the force depended on the electric field strength. The electric field strength is now greater because the potential difference is greater because E was V over D, and so we are expecting that X will be higher up than it was before. Okay, so we explain that. So often the explanations, remember, link to previous things you worked out. So there's a higher position. Why? Well, there's a greater electric force or there's a greater electric field strength. So there's greater acceleration, hence greater displacement. Okay, finally, we're going to come back to something that we considered at higher, which is the electron volt as a unit of energy. The work done in moving an electron through a potential difference of 1 volt is 1.6 times 10 to the minus 19 coulombs because W equals QV. This is called an electron volt, a small unit of energy, but it's often quite useful to look at because 100 electron volts will be 100 times this amount, so you can get a better feeling upon it, in the same way that we use light years instead of meters for distances in astronomy. Okay, so you have to have an appreciation of what that is and then convert between the two from there, and you do that just by multiplying by the number of joules in an electron volt, which is 1 electron volt is Q times V, so it is charge on an electron times 1 volt. So here's a particular question. We have muons detected at sea level. They have a particular energy, 4.1 giga electron volts, and we're asked to work out what is the total energy in joules every second if we record 10,000 of these in 1 minute. So to convert between the two, we say we've got that many electron volts. 1 electron volt is the energy needed to accelerate an electron through 1 volt, Q times V. So the energy of 1 muon is our EV times 1.6 times 10 to the minus 19 in terms of joules. And we have 10,000 of those in a minute. And so the amount we get in a second is a 60th of that. Okay, so what we've looked through in this video is we've looked at solving problems of charged particles in uniform electric fields and then briefly mentioned the electron volt.